and we have a point D. So at point A, right, what we see that for von Mises, stress A, point A, and stress at point B, both are at the yield. For Tresca, it's the same. Stress at point A is equal to stress at point B is equal to stress at point yield, right? And then if we look at point B, right, if we look at point B on the stress A, stress B graph, you also see that stress A is equal to stress B is equal to minus stress U for von Mises, right? They have the same point, and then we have stress A is equal to stress B, and this is equal to minus stress U. Now, if we look at point C now, right? If you look at point C now, right? At point C, what will happen is you will see that minus stress A. So stress A is negative, right? And this is equal to stress B. And at this point over here is equal to minus, right? It's equal to minus 0.577 stress U. Okay. Whereas for Tresca, stress A or minus stress A is equal to stress B. This will become 0.5. Okay, it's equal to 0.5 stress U. Okay, I'm going to get rid of the minus. There's no minus sign down here. I do apologize. Okay, and then if you look at point D, again at point D, stress A is equal to minus stress B, and this is equal to 0.577 stress U. And then at point D for Tresca will be equal to stress A is equal to minus stress B, and is equal to 0.5 stress U. Okay, so from here, looking at the numbers over here, right, we know why Tresca is half. Yes or no? Right, Tresca is half is because we have maximum shearing stress. Right, so if you look at point B, C, and point D, right, and if you look at the value over here, what we can say is von Mises in shear or von Mises is less conservative than Tresca. You can see that already. Okay, now let's look at a condition, right? So what we see down here, we have a condition where at point C, at point D, right? What is going on this straight line? Okay, we want to see what is going on this line. Okay, let's consider what is going on for line C, point C to line point D. Okay, so let's look at this. Okay, so we realize that over here, right, and over here, this value is exactly what? Half. Right? This value is exactly half. Exactly. Or if you can look at either scale, okay, either axis is still half of the stress U. So what is going on down here? When is it possible that it's going to be half on most circles? So let's look at Tresca. Oh, sorry. Let's look at Tresca at at or along at point C and point D on most circle. Okay, so at what stage will happen where stress C and stress D or point C and point D, right, over here, correspond to what we see on Mohs circle. Okay, so at state C and state D on Mohs circle, right, the principal stress have to be half of the yield. Okay, so when that is possible. So now I'm going to draw Mohs circle now. Okay, we're going to construct Mohs circle now. So I'm going to draw Mohs circle. So this is element, the shear element rotate clockwise, the shear element rotate anti-clockwise. This is our normal stress, and I'm going to sketch in our operating boundary. Okay, so this is our operating boundary. I'm going to draw it bigger. So this is our operating boundary. Okay. So at this point down here, we know that this is our stress U. At this point down here, this is our negative stress U. So what we state that stress A and stress B has to be half. Okay, so this is half. This is minus half. So from here, we can draw our Mohs circle. Okay. This is our Mohs circle. Right? So that's our Mohs circle. And we can say that over here, so if we look at our element now, right? If we look at our element now, right? And if we were to call this point X, and we were to call this point Y, in what condition on our stress on our element, then we can construct a circle like this? Anyone? At what stage? And can anyone answer me, please? When, again, what is our stress state? Okay, so what is our stress state is when we can construct a circle where stress, the circle will be exactly at the center, including at point Z is over here. Okay, remember we are dealing with what? 3D. Okay, so can anyone answer me that, please? When can we construct a circle like this? There are two conditions, yes or no? Anyone?
One of the principal stress states is 0.
Okay, so condition number one is this. Okay, so condition number one, you're partly right. Okay, condition number one will occur when stress X is equal to stress Y, right? So stress X is equal to half of stress U, and stress Y is equal to minus half of stress U. So i.e., for condition number one, this is where your point X is, X1, okay, for condition number one. So this is our X1, and then this is our Y1, condition number one. Okay, Y1. Okay, and then condition number, so if we were to sketch our element will look like this, our stress state, where we have a stress over here. So this will be going by tensile, which is stress Y over 2, stress U, and this will be stress Y over 2. Okay, then you can construct a circle like this. Condition number two is where you have stress X is equal to stress Y. Both of them are equal to what? 0. And however, you have your shear XY is equal to shear YX, and this will be equal to stress Y or stress U divided by 2. Okay, so the other condition is where your element will look like this. It can be either positive or it can be negative. So when that's the case, right? So I'm going to call this x2, y2 now. Okay. So now the point changes to over here. So x2 and over here y2. Okay. So along CD line, along this line, right? Okay. That is where, so along CD line, that's where over here you see what? You see von Mises. Okay. Sorry, you see Tresca. Okay. Where over here you see Tresca. And then when you draw von Mises, right? Your circle can now become what? Bigger. Yes or no? Because now this value is no more 0.5. Now this is 0.557. Yes or no? If you draw the lines down here now it's 0.557 stress yield. And over here is also equal to minus 0.577 stress yield. Okay. Now, why 0.577? Okay. Now the thing is why 0.577. Okay. So very important, there are two conditions now. Okay, two conditions where the circle will look exactly like this. Okay, so now we're going to look at the condition. So how do we get? So the next one is how do we get? Okay, the next one is y 0.55. So how do we get 0.577 stress yield? Okay. Okay. So we're going to put the structure under pure shear. So condition number 2 that you see over here is what we call what? Pure what? Pure shear. Okay. Pure shear will occur when the structure is under torsion only. Okay. So what do I mean by torsion only? You have a structure over here. Now this structure is under a torque. Okay. So this is what. So you apply a torque, a pure torque. Okay. So a twisting. No normal stress, no bending stress, just a pure what? Just a pure torsion. So when that's the case, right, we have seen it. So if we were to sketch this element out, what we see is stress A, right, will be equal to minus stress B, right? Like what we see over here, right? Stress A, right? Stress B. Okay, so stress A is equal to minus stress B, right? And then we're going to so stress A equal to stress B, and we're going to substitute into equation number 1 now. Okay, so sorry, substitute into stress A squared minus by stress A, stress B minus by stress B squared, and is equal to stress U squared. Okay, so once we have this, right, so we're going to say this is going to be stress A squared, right? So this will be equal to plus by stress A squared, right? Because stress A, so once this term's over here, it becomes plus, right? And then the third term over here is plus by stress A squared, and this whole thing will be equal to stress U squared. Okay, so this will be equal to 3 times or 3 stress A squared is equal to stress U squared. So stress A squared is equal to stress U squared divided by 3, right? So stress A squared or stress A now is equal to plus or minus stress U divided by square root 3. Okay, stress U divided by square root 3. So this will be equal to plus minus, so 1 divided by square root 3 is 0.577. Okay, so that's where we have shown why when we have stress A and stress B at point C or point D, we get what? 0.577. Okay, right. So I think I've bought you enough with 1 hour worth of theory. Okay,